Right, so a little bit, we've been talking about how fast molecules were moving, and then we also talked about the kinetic molecular theory of gases and how we just kind of make those blanket statements for gases because their deviations from that are really, really insignificant. Now, we can measure those deviations, and not all gases are perfect or ideal. There are real gases. Some of them have real interactions, and some of them are really big particles. So sometimes we do need to take those into account. So we're going to talk about deviations from ideal behavior. So you can use Pivnert for ideal gases. It's pretty darn good. However, there are some factors that cause deviations or differences from ideal behavior. And that is at different pressures and temperatures, they can start deviating. So at really high pressures and really low temperatures, we see gases start to kind of act not ideal. Because if you think about it, at high pressures, you're kind of like condensing them. They're just start running into each other more, right? A really small volume or something. They're getting really close together, and they're going to start to interact with each other and become less and less ideal. They're going to start bouncing off each other. You're going to get less elastic collisions. You're going to get attractions, and it's going to cause problems for your calculations. So under really high pressures and under really low temperatures, when they start to slow down, they'll start interacting with each other more. You're going to get deviations. So gases deviate at high pressures and low temperatures. They're actually much more ideal and much better at low pressures and high temperatures, where they can move fast and they can spread out. They don't interact with each other. So this is when they start acting less ideal. So we actually have graphed this. So if you're kind of wanting to know like where and why when they change and stuff. So this would be an ideal gas, okay? It would have a ratio of 1 if you did PV over nRT. This is like the perfect gas. And notice as the pressure changes, as they become, so this is where they're all closer to ideal right here. The higher the pressure, the more they're going away from or deviating from an ideal gas. Okay, under high pressure, they're going to start interacting with each other. Also, you can see at very, very low pressures, there's a couple that kind of go wonky, the C2H4 and the CO2, those are for different reasons. But the higher the pressure, the more they deviate. These guys up here are pretty close to ideal, and then everything starts to go crazy. So high pressures, bad. Okay, now if we look over here, we're looking at the same thing. This is my ideal gas. And my pressures at very, very, very low pressures. These guys are all very close to ideal. This is just a zoom in of like right here, right? Carbon dioxide is a little bit unideal, but it's like that a lot because it's a little bit bigger of a molecule, and there's other reasons for that. But for the most part, gases are ideal close to at low pressures. This is a good thing. Okay. So how do we take into account that there are these differences? Well, we use our very last gas law called the van der Waals equation. It's going to account for molecule size and attractions. It's going to take into account the fact that some molecules are bigger than others and take up some of that volume, and that some of them do have attractions if they're polar. So this is our nice new equation, and I know it looks gross, but we're really just going to be plugging and chugging with this, okay? It looks a little bit like Pivnert. I got a P, I got a V equals nRT. The only differences are these variables here, okay? So this is like your fix for the pressure, and this is like your fix for the volume. The fact that their pressures and volumes differ slightly because they might be big or polar molecules. So A and B are the only new things being introduced here. N is still moles, V is still volume, N is still moles over here. A and B are constants that you can look up for specific molecules to fix your Pivnert equation. So like carbon dioxide, I told you it's acting a little non-ideal here. If you look up its A and B values, they're actually a little bit bigger. You plug them in here, and then you can calculate much more accurate things for that gas, the pressure, the volume, or the temperature. Okay, so van der Waals constants, for example, I said you can look these up, right? A and B values, you don't have to know what the units are. Everything's going to work out. These are things you can look up. Okay, you'll see xenon here has a very, very large A, and compared to the other ones, a pretty large B value as well. Also CCl4, a very large A and a large B value as well. And that's because these are really big. Okay, they're going to definitely have deviations from your ideal gas law. Okay, so a lot of the times what I'll ask you to do is calculate using the ideal gas law and then calculate using the van der Waals equation and see how different they are. okay, which is what example number 19 is. So I would like you to try example number 19 and compare the two. Okay, so in part one, I use the ideal gas law, which is just Pivner, plugged in my volume, plugged in my moles, my R, my temperature, and got 33.5 atmospheres. This is the pressure of this carbon dioxide at ideal conditions. We know carbon dioxide isn't ideal all the time. So using the van der Waals equation, I'm going to calculate its pressure more actually, okay, more realistically. So I need my A value and I need my B value, which is in this table here. My A is 3.59 and my B is 0.0427. So I plug those in here, calculate, yes, lots of algebra, I know, solve for P. The pressure I get using the van der Waals equation is 32.4 atmospheres. So it's actually, its real pressure would be 32.4. So it's a little bit different than what we see ideally. Technically, the pressure is in reality a little bit lower. And that's because CO2 is a pretty big molecule and it has some attractions because it's a big molecule. So this is a more realistic view or measurement for carbon dioxide.